Hello students, this is the recording for the 5A lesson on solutions and concentration. Alright, so go ahead and take a moment to stretch your brain and think about which of these glasses here, 1, 2, 3, 4, 5, has more drink mix in it, and think about how do you know that is true. Go ahead, pause the video and continue playing when you have an answer. All right, so taking a look here, you probably said that the one with more drink mix is the darker one, and if so, that's probably correct. The reason why is we know that generally as we add more drink mix to a drink, it gets darker, it gets sweeter, it gets more flavorful, right? So those are some of the traits that we can use to identify or observe that it has more drink mix, right? So the darker one indicates that there's what's called a higher concentration of that drink mix, right? It has more of it in there. All right, so let's go ahead and take a look here. There are only 10 days left of trimester 3, so please make sure that you are focusing on getting your projects done. Remember, projects are worth 70% of your grade. It's impossible to pass without them, and you need to get them done, right? So we're going into Unit 5. Unit 5 is super duper short, just taking a look at solutions and concentration, factors affecting solubility. We'll talk about acids and bases, and then wrap up Unit 5. So taking a look here, it's a very short unit. Don't forget that your final exam, your last exam, not really a final because it's not comprehensive, but your last exam, units 4 through 5, will be due on Wednesday, May 2nd. It'll be zeroed out then on Thursday, May 3rd. So you have a bit of a grace period there, but again, remember that projects plus this exam are worth 70% of your grade, which means that each one is worth about 17.5% each. Again, it's impossible to pass without them. Don't waste your time on other things at this point. You need to focus on those big things. If you're just trying to turn in a bunch of notes, that's going to be a waste of your time. Notes are not worth very much compared to a project and an exam. This is a reminder that your last STAR 360 assessment is on Wednesday, which should be tomorrow for you. It is worth 5% of your grade in every single class, so make sure that you get both of them done, both reading, which was due today, so make sure you get that done if you haven't already with your academic advisor, and then math will be on Wednesday during whatever your normal period 3 class is. Please keep in mind that you're still responsible for any lessons that you miss during this testing time because it's only the single test. The test only takes 20 to 30 minutes. So we're not excusing that work. You still need to make up that work. So just watch the recording in our class in order to do the notes. Remember that we did have an exam originally planned for this Tuesday. However, we've moved it, so we're just going straight into Unit 5. And then the Unit 4-5 exam will be combined here again on Wednesday, Thursday, and then you'll have a week to make up anything that's missing, again, focusing on projects and exams so that you're not wasting your time, so that you're not wasting our time. Make sure that you're focusing on those things. At this point, don't forget that I am now on maternity leave and that you are on Mrs. Smith's roster. However, if you do need help on the projects, make sure to reach out to Mr. Bangle since he's been with us the entire trimester and knows what the science projects are about and can help with those. The substitute doesn't have as much of a background in science, so she can direct you around, but if you need individual tutoring, definitely reach out to Mr. Bangle. His contact information is right here. All right, so today we're going to be able to define a solution, solute, and solvent, define concentration of a solution, and identify methods by which a solution can be physically separated. And you should be working on your 5A notes, so if you haven't already, make sure that you have opened up your 5A notes and click Start Quiz. If you weren't in class, to get the links, everything is in your Grades tab, so just go to your Grades tab and you'll find that right there. Okay, so let's go ahead and take a look at this brainstorm. What do you observe happening in this diagram and why do you think that might be happening? Go ahead and pause the video, continue playing when you're ready with an answer to both of those questions. All right, so taking a look here, what you should be able to see here is that there's something called, there's some sort of separation going on, right? So we start out with a mixture of water and sand right here. You can see that there's this filter paper inside of a funnel. So it's kind of lining the funnel. It might be a little bit hard to see, so let me draw it out. So there's a filter paper lining that funnel, and you can see that water is moving through that filter paper and then going through the funnel into the lower container, into the beaker. And then on top, you can see that the sand is not going through that filter paper, so it's kind of staying on top inside of the filter. So for some reason, the filter's allowing the water to go through, but not the sand. And what this has to do with the size of the particles, right? So sand has much larger particles, whereas water has much smaller particles, right? They have liquid particles that are going to be able to move a little bit more easily through that filter. Okay, so we can see that there is separation going on. Now, why is that important? We'll talk about that in just a moment. But again, just to review, water can go through the filter because it has smaller particles. Sand cannot because its particles are too big, and this filter allows them to be separated. And again, this idea of being able to be separated through something physical like a filter paper, all right, is going to be important for today's lesson. All right, so let's review mixtures. This is all the way back from unit number 1. Remember that mixtures are when we have different types of matter that are physically combined or blended. Remember, any time we're talking about physical stuff, this means that chemicals are not changing, right? So nothing is chemically changing into different chemicals, right? So if I mix, for example, salt plus water, it's still going to be salt water, right? It's still just salt and water. At no point is there a chemical reaction, right? So without chemical reactions, there's nothing that's going on to change the identity of that water, right? The water is going to be H2O still, and the salt is still going to be sodium chloride, NaCl. So again, their identities are not chemically changing. In the same way, we're talking about this idea of separation during our brainstorm today. So these things, since they're physically combined or blended, can also be physically separated. For example, with the filter paper, which we'll talk a little bit more about at the end of this lesson. So again, you can see some examples here, right? We can see some chocolate pieces that are being physically combined, very distinct parts to it. You can also see right here some examples of like concrete, which is like rock and cement mixed together. I might have gotten cement and concrete backwards. I always mix those up. But again, you can see that they are being physically combined. Therefore, they can be physically separated. Again, nothing is chemically changing here, okay? A really good example here is, for example, sulfur and iron filings. Remember that sulfur is a nonmetal, okay? A stinky nonmetal if it bonds with something, whereas iron filings are definitely metals. Now, again, these ones are not actually reacting together. We're just combining them. And since they're not reacting, there's nothing chemical going on. That means that their mixture is still right here, just iron and sulfur, right? Again, everything is still chemically the same. So that means you can also go physically just separate them. And this way is another way that you can physically separate things, which is with a magnet. So the magnet will attract the metal, but not the nonmetal. And so that way we can physically separate that metal. So again, if it's physically combined, if it can physically be separated, that is just a mixture. There is no chemical reaction going on. All right, so at this point you should be able to answer this question. It says box all of the correct statements about mixtures. Here are your options. Mixtures are physically blended. Mixtures are made up of only a single type of matter. Mixtures must be separated by a chemical reaction. Mixtures can be physically separated, like with a magnet, for example. Go ahead, pause the video, think about the correct answers here, and then continue on when you feel like you have a good answer. All right, so taking a look here, correct answers are that mixtures are physically blended. Again, there's no chemical changes. You're just physically putting together different types of matter. And that mixtures can be physically separated. Again, like with our magnet, able to pull out a metal from that mixture, leaving behind the nonmetal, or filtration, right, the filter that we saw earlier. Now, mixtures are made up of only a single type of matter. That's definitely not true. Again, we said that it needs to be a mixture. It needs to be more than one type, right? So needs more than one type. And mixtures can be separated by a chemical reaction. That's definitely not true. There are no chemical changes. This is going to be the answer to number 2. Make sure you pause the video and continue playing once you have number 2 answered in your 5A notes. All right, so let's talk a little bit about the different types of mixtures. Again, we will be getting into why this is so important in just a moment. I know this is a lot of review, but remember that there were two types of mixtures we learned about: homogeneous mixtures and heterogeneous mixtures. And the cool thing about science is a lot of times we try to name things in very obvious ways. So remember that homogeneous, the prefix homo here means same. And so a homogeneous mixture looks the same throughout, right? This means that it's blended very uniformly, and that if I were to take a sample from the top, the bottom, the middle, the sides, every sample would look identical. So every sample is identical. And you can see there's like no distinct parts, right? So no distinct parts that you can actually see. Okay, so that I'll drop that over here. Now, heterogeneous mixtures, on the other hand, the prefix hetero means different. All right, so again, this helps us to remember its definition. So these ones are blended non-uniformly, meaning that there's very distinct parts to it, or that, for example, if you were to take different samples, each sample would be a little bit different, okay? So homogeneous mixtures, just so you know, are also called solutions, which, if you remember from our objectives today, we are defining what a solution is, so this is why this is important to review. So homogeneous mixture can also be called a solution. Again, it looks exactly the same throughout, hence homogeneous. And there are no visible particles. Again, there's no distinct parts. You can't see any rocks, you can't see any M&Ms. Everything is blended very uniformly. So for example, when you mix salt with water, eventually that salt dissolves and you can't tell where the salt went, right? It looks the same throughout, it's completely dissolved. Now, heterogeneous mixtures, some examples again, they look different throughout. You can actually see the visible components. Example here is oil and water, right? This top part is definitely more oil. This bottom part is definitely more water, and so those samples look different. You can tell that there's oil and water. Same thing over here, you can see an example of sand or gravel. There are distinct pieces, right? I can actually pick out the black pieces, the white pieces, the yellow pieces, the brown pieces. I would be able to actually separate those. So that is a heterogeneous mixture. Each sample is a little bit different looking. Okay, so that brings us to this idea of solutions. Let's break down solutions even further. Again, we just learned that solution is another word for homogeneous mixtures, which are uniform mixtures that look the same throughout. And there are two terms that you need to know that go along with solution. So you need to know that a solution is a mixture of a solute and a solvent into a single phase. Now, what does that mean, a single phase? Well, let's think back to the phases that we learned about. We learned about solid, liquids, and gases. And what happens is, in a solution, everything gets mixed together, and so it appears to end as a single phase, one of those, only one of those. Either it's solid, either it's liquid, or it is a gas. All right, now you might be wondering, how is that possible? Let's take a look at some examples here. So solids, for example, brass is a type of metal that is in fact a solid version of a solution, which might be weird. Again, you might think of solutions as being liquids, but you can actually have it solid solutions. So the reason this is still a solution is because copper is one of the metals and zinc is one of these metals, and they get mixed together and they create a solid that looks uniform throughout. Again, you cannot visually tell the difference between the copper and the zinc within brass. It's all blended so uniformly that every single sample looks identical. Now, liquids we're probably a little bit more familiar with. So for example, sugar, water, and carbon dioxide gas all get mixed together into soda. And so that soda is in a liquid phase. Eventually that gas does come out once we open up the bottle, but for a while, when the bottle's closed, that dissolved carbon dioxide gas, you can't see any bubbles. It's stuck in there, and it's all appearing as a single liquid that is very uniform. Every sample is identical, so that does count as a solution. Again, even though you start off with different things, right? Here, sugar is a solid, water is a liquid, carbon dioxide is a gas. They all get combined into a single phase, in this case, liquid. An example of gas would be just air in general. So air is about 70% nitrogen, 30% oxygen. And so mixing those together, along with a little bit of argon and some other gases that are existing in very small amounts in our atmosphere, those all together make air. And again, you cannot tell the difference between different samples of air, right? They are all very uniform, all right? If we look at it, if we look at air, we obviously don't see any difference, all right? Even on a small level, different samples are going to look the same within the same area. Okay, so this is important to understand the difference between a solute and a solvent. So solute is always what you have the least amount of. So this can be a little bit tricky because, for example, right, in brass or in a different type of metal, right, you could have more copper and less zinc. And in that case, your zinc would be your solute because it's what you have less of. But if you were to have less of the copper, then the copper would be the solute. So technically, it's literally whatever you have less of, okay? So the substance of which there is the smallest amount, it's technically what is getting dissolved, okay? The thing that is getting dissolved into the solution. You can see an example of this right here. So we can see a solid solute that we have a lot less of. All right, this is going to be our solute. You can see that over here as well. Okay, now the solvent, all right, is the substance of which there's a larger amount, and this is what is doing the dissolving. So again, if you think about our brass example, if you have more copper, then now your copper is your solvent. If you have more zinc, then now zinc is your solvent. Now generally though, when we're talking about liquid solutions, then we're talking about water, something dissolving into water, and water is usually your solvent, right? So water is what we call the universal solvent because it is the best at dissolving everything in our earth. It does not actually dissolve everything, but it does dissolve the most things, hence universal, okay? So again, solvent is what we have a larger amount of. This is what is doing the dissolving, all right? So let's go ahead and take a look at an example here. You can see that I have, oops, sorry, I want this one. You can see that I have a cup of water and I have some powdered drink mix here for lemonade iced tea. I'm going to go ahead and pour that in there. All right, and mix it up. And what you'll notice is that as this begins to dissolve, eventually each part of this will look uniform. So the top will look the same as the bottom, which will look at the same as the middle and the sides. So that makes it a solution looking completely uniform in a single phase, in this case liquid overall, right? Our powdered mix starts out as a solid, our water starts out as a liquid, but once it becomes a solution, it's now a single phase, which in this case is the liquid phase. Okay, so taking a look here, you should be able to identify what is the solute and the solvent. Again, the solute's what I have less of. So think to yourself, did I have less of the powder or less of the water? Okay, and then the solvent is what I have more of. So again, think about what do I have more of, the powder or the water. Pause the video, continue playing, and we'll go over the answer in just a moment. All right, well, hopefully this makes a lot of sense because we already just discussed about how water is generally our solvent in a solution because it is the universal solvent, right? So again, this is definitely what we had more of. I had way more of the water, and so the water was most definitely my solvent in this example. On the other hand, the solute, what I had less of, I had a lot less of this powdered mix, drink mix. So the powdered drink is definitely what I have less of. It's what's getting dissolved, and therefore that is my solute. All together, once we have the solute and solvent mixed together, again, that makes our overall solution. So that's how you differentiate between solution, solute, and solvent. Solution's what you have overall, solute's what you have less of, solvent's what you have more of, mix them together, you get a solution. All right? This is going to be the answers to number 3 and 4. Go ahead and fill in the blank for number 3 with the word single. Capitalization does not matter, but spelling does. And then number 4, fill in the blank with the word universal, only the word universal. Go ahead and pause the video and continue playing when you're ready. All right, so now it can be a little bit tricky to remember all of these because they look very, very similar to each other, but there is actually a very easy memory trick that can help you to remember which one is which. So what I want you to take a look at is I want you actually to take a look at each of these terms, solute, solvent, solution, and I want you to actually count up how many letters do you see in each of these words. Pause the video, continue playing once you have an answer for each word, the number of letters that you see there. All right, so let's go ahead and take a look here. You should see 1, 2, 3, 4, 5, 6 letters in the word solute. You should be able to see 1, 2, 3, 4, 5, 6, 7 in the word solvent. And 1, 2, 3, 4, 5, 6, 7, 8 and the word solution. And this right here is the trick, y'all. So the short word, in this case with only 6 letters, solute, is what you have less of. So this is actually what is getting dissolved. It's what you have less of. It's a short word. Short word's what you have less of. So this is what gets dissolved. For example, my drink mix in the example that we looked at earlier. Now solvent is our medium word, and so this is what's doing the dissolving. This is what we have more of, right? It's a bit of a longer word, okay? And this is what is doing the dissolving. So this is going to be my water. Again, water being the universal solvent that we discussed earlier. And then solution is the longest word with 8 letters, and that is just everything put together, right? So we have the short word, what we have less of, the medium word, it's getting mixed into, what's doing the dissolving, and then the long word is just putting it all together. So the final result of our solute and solvent together, right? We're adding these together to make our solution. So this is a really good memory trick. Make sure you keep this in mind. It will help you be successful here. Shortest word is what you have less of. Medium word is what you have more of. Longest word is the final result. Okay, so let's go ahead and jump back to thinking about our brain stretch today. So our brain stretch, we were taking a look at this picture down here and trying to think about which of these has more drink mix. And we identified that the one that's darker definitely has more drink mix. Now the reason that you know that is because you've probably used drink mix at some point in your life, and you know that the more that you add, the darker the color gets, the more sugary it gets, the more flavorful it gets. Now this leads us to this concept of concentration. So concentration is the ratio, meaning kind of like the amount per amount of the solute in a solution. So it's the solute per solution overall. Again, solute being what's getting dissolved, right? It's our short word. Solute gets dissolved like our drink mix, okay? Now, concentration is going to increase with the more solute that you have for the same amount of solvent, right? So if I have just 1 cup of water and I'm adding more and more of the solute, then it will become more concentrated, just like we see right here, right? These all have the same amount of solvent, which is our water. But as we can see over here, we have more solute, which is our drink mix, and that makes it more concentrated. So the more and more solute you have for the same amount of solvent, the same amount of water, the more concentrated you are. High concentration, again, means you have more solute. Low concentration would be less solute. That's also what we call diluted. You can see that right there. Dilute is another word for less concentrated. You can also see an example over here where the solute here is the blue stuff, and you can see there's a lot less blue in the dilute solution, where there's way more blue particles, way more blue solute particles in our concentrated solution. Now, you cannot just dissolve things indefinitely forever, so this is important to understand that if you've ever played with sugar at a restaurant, for example, while you were bored, as you add more and more sugar to a solution, eventually the sugar stops dissolving. So this is what is called saturation, or a saturated solution. So solute will dissolve until it can't dissolve anymore. If there's no more room for additional solute, then all that extra stuff is going to kind of sink down to the bottom. And you can see an example of this right here, right? You can actually see some additional solute right down here at the bottom that has not dissolved. So this right here again, up here then, is completely saturated. It has as much solute as possible in it. Let's go ahead and take a look at an example, a virtual example of this. I'm going to go ahead and pop this up on the board for us. Okay, and we're going to go ahead and take a look at what happens to a solution as it reaches saturation. So I'm going to go ahead and put the concentration meter in here. I have some drink mix. I'm going to go ahead and add this in. And you can see it's starting light red. And it starts to get darker and darker. You can see the concentration meter increasing. Again, we know that the darker it gets, the more concentrated it gets, right? We have more solute. All right, concentration continuing to go up. We don't really talk about this a lot, but the units for concentration here is moles per liter. And we learned about what moles were. So the number of moles per the liter of solution is the concentration here. So you can see it's getting very, very dark. All right, we're going to go ahead and keep going there. Keep going. And now look, it's saturated. Now the reason you know it's saturated is because at the bottom, it might be a little bit hard to see, but at the bottom you can see that little particles of that drink mix are no longer dissolving. So you can actually see that some of that drink mix is still around. And so again, this means that the rest of the liquid is now saturated. It cannot fit any more solute. All right, that's going to be the answers to number 5 and number 6. So again, concentration increases with more solute. Fill in the blank with the word more over here. And then number 6, once you have so much that no more can dissolve, that is called a saturated solution. Capitalization does not matter, but spelling does. Pause the video, continue playing when you're ready. All right, the last thing we need to talk about is how do we separate solutions? Because remember, we talked about the fact that solutions are only physical mixtures, right? They are homogeneous physical mixtures, which means that we can also separate them physically. Now again, we've already talked about a couple examples here. So we talked about the magnet being able to separate a metal from a non-metal that has not chemically reacted. They're just combined physically. Another example we took a look at is filtration. All right, so filtration is when we have a filter and the solute can be filtered from the solvent. So in our example earlier, we saw sand was what we had less of, so that would have been the solute. Water is what we have more of, that would have been the solvent, and we can actually go ahead and filter that with a filter here. So the larger particles get trapped on top, right? So those ones can't go through, and then the small ones can go through, and that allows physical separation. So that way all the big ones end up on top of our filter and all the small ones end up underneath our filter. Again, just a physical separation. There's no chemical changes. The sand is still sand. The water is still water. Now sometimes the solutions, again, you can't necessarily see the solute unless it's overly saturated, right? Unless it's saturated. And so because they're so uniform, sometimes it's hard to tell that you can physically separate them. So an example here is salt water. Salt water doesn't seem like it can be physically separated because the salt's dissolved into the water. All right. However, it can still be physically separated using a process called evaporation. And evaporation is, in fact, only a physical process. It might seem super sciencey, but there are no chemical changes going on. The salt is still chemically salt, sodium chloride, and the water is still chemically water, H2O. So what we can do is we can evaporate the solvent, which in this case is the water, using heat or sunlight, and that will go up into the atmosphere. Or in this case, you can see here they actually collect it, right? So the evaporation turns it into a gas, so it goes up, and then you can actually cool that back down into clean water here. And the solute, which in this case is the salt, what we have less of, the shorter word, solute is shorter, gets left behind. All right, so this is a process called desalinization. If you've ever heard the word saline, like a saline bag in a hospital, saline is salt water, okay? So once this gets separated from the solution, the salt is now able to reform into its normal salt. Again, there's no chemical changes here. It's still chemically sodium chloride. You can see down here, you can actually really easily use this to your advantage to make a survival distillation process here. So what you can see here is we have dirty water and salt water here. And what you can see is that they're kind of leaning up a little bit. So as the water gets evaporated by the sun, it goes up into this top bottle, and then it cools down and it drops down to the bottom here and gets trapped in this little area right here. So that'll be your clean water that got evaporated and separated physically. And what's left over is eventually you'll just have your salt or your dirt left over on the bottom. So I would recommend, if you want to do this experiment, make sure you use salt water. There's some things in dirty water that can't be completely cleaned from sunlight, but salt water that you make it won't hurt you, right? So that's something that you can actually do at home. All right, so this is going to be your last question. This one you do need to complete on your own. We talked about filtration, solution, solute, solvent, and desalinization. Figure out what gets dissolved like our salt, what does the dissolving like water, what is also known as a homogeneous or uniform mixture, What is a physical method where water gets evaporated from salt? And what is a method where a barrier separates large and small particles? Go ahead, pause the video, answer question number 7, and continue playing when you're ready. All right, so at this point you should be able to define solution, solute, and solvent. You learned a little bit about concentration as well, and you learned a few physical methods by which we can separate those solutions, because again, solutions are only physically mixed, therefore they can also be physically separated. Hopefully you got a 80% or higher on your 5A notes. Pause the video, reflect, think about where are you at on today's understanding. Excellent. All right, so if you are in the very confused or still need some help area, remember, please reach out to Mr. Bangle so that you can get some private tutoring, some individual tutoring to help you get any misunderstandings figured out. All right, make sure that you submit those 5A notes, and again, I hope you did well on that, and we'll talk to you later.